All right, so now I've started recording. Let's come back to this share screen QuickTime Player. All right, so Rishikesh, you had a question. You wanted to see the slide, is that right? Are you there? Where did he go?
I'm here, sir. Yeah,
Okay.
I'm going. Yeah.
By the way, sometime back a suggestion had been given that after I write, I wait for a few seconds. Would you like me to do that? If it's going too fast, I don't mind. I can take a breather for a few seconds while we just take a little time to digest it, because this goes faster than writing on the board, right? So if you want, I'm happy to do that.
Yeah, sir. Maybe specifically for the definitions part where you
Okay.
define something. Yeah.
Okay. So let me just wait for a second. If you have a specific question, you can ask.
So you can go forward.
So please do keep this feedback coming, because I may not, I may not be realizing that I'm going too fast. So it's very helpful when students point out. Okay. So now let's look at the case. So once again, we're back to this thing, right? We want to show expectation f of x times gy is expectation f x times expectation gy. We have already shown this when f and g are non-negative simple. Next step is to show it for f and g non-negative measurable. So step 2, suppose f and g are non-negative measurable functions. So now again, we will use the familiar trick. If I have a non-negative measurable function, I can always find an increasing sequence of simple functions which converges to it pointwise. Okay, so suppose phi n going from 1 to infinity is a sequence of non-negative simple functions which increases pointwise to f. Similarly, we have a sequence psi n going from 1 to infinity, which is a sequence of non-negative simple functions which increases pointwise to g. We know that such sequences exist. All right. Now, just to be clear, here f, g take the real line to the real line. Of course, phi and psi n also take the real line to the real line. Okay. Now, since phi n increases to f, what does that mean? That means that for any real number small x, the sequence of real numbers phi and x increases to the real number f of x. Okay, in particular, for every omega, remember capital X of omega is going to be a real number. What we're saying here is that for any real number, phi n increases to f. In particular, if the real number I take to be x of omega, then phi n x of omega is going to increase to f of x of omega. This is for all omega and omega. Okay, so what this is saying is, thus phi n composed with x increases to f composed with x. Now remember that phi n composed with x and f composed with x, what is their domain here? This is omega, not the real line, right? This is a composite function. All right, similarly, since psi n increases to g at every point, psi n y of omega increases to g of y omega for every omega and omega. So psi n composed with x increases to, no, not composed with x, composed with y increases to g composed with y. All right, now if this sequence increases to this limit, this sequence increases to this limit, everything is non-negative, then the product of these two guys must increase to the product of these two guys. Okay, basically I'm saying if AN increases to A, BN increases to B, and everything is non-negative, then AN, BN increases to AB. That's what I've written here. So phi n x of omega times psi n x of omega increases to f of x omega g of y omega for all omega and omega. So far, so good. Now remember, phi n is simple, psi n is simple. So by step one, what do you know? You know that expectation phi n of x, psi n of y is expectation phi n x, expectation psi n y. So this equation one comes in because of independence and what we've done in step one already. Okay. All right. So also, what do you have by monotone convergence theorem, right? So by monotone convergence theorem, you have limit n goes to infinity, expectation of phi n of x equals expectation of f of x. Right? Why is this true? This is true because phi n of phi n of x increases to f of x. Everything is non-negative, so you can use monotone convergence theorem. Similarly, by monotone convergence theorem, limit as n goes to infinity, expectation psi n of y equals expectation g of y. Again, why is this true? This is true because of monotone convergence theorem, right? Where am I? Yeah, psi n of y increases to g of y. And remember, expectations are just integrals. And also by monotone convergence theorem, limit n goes to infinity, expectation phi n x psi n y equals expectation of f of x g of y. Right? Again, this is monotone convergence theorem at work because phi n x multiplied by psi n y increases to f of x times g of y. Yeah, and that is written over here. And again, everything is non-negative. So now you just put the pieces together and expectation of fx gy must be expectation fx times expectation gy. All right, so you put these pieces together to get the desired result. Any questions with this? All right, so now we'll extend it to real valued functions. Now remember again, so far we have had no need to use integrability. Okay, so remember when we started the show, we put this assumption that expectation absolute value of fx is finite, expectation absolute value of gy is finite. So far we have not had to use it because so far we were saying that the functions have to be non-negative. So if any integral diverges, that's fine. You'll never get infinity minus infinity. But now if you want to look at real valued functions, then you have to put this thing because you never want to allow infinity minus infinity. All right, so and then the rest is straightforward. So suppose f and g are real valued, right? I can decompose f as f plus minus f minus. I can decompose g as g plus minus g minus, right? Now, what do you know? So expectation, actually, let me do the following. Absolute value of f of x, this is going to be f plus x of f plus x plus f minus x. I'll leave it to you to check this. Okay, absolute value of f of x is going to be the positive part of f evaluated at x plus the negative part of f evaluated at x. Right, I mean, this you can see why this is true, right? Absolute value of f is f plus f minus, right? So the absolute value of a function is the sum of its positive and negative parts, no matter where you evaluate it. So in particular, if you evaluate it at x of omega, the absolute value is going to be the sum of the positive and the negative parts. Any questions with that? All right, and now remember we have been told that now this guy is non-negative, this guy is non-negative. We made the statement that don't be fooled by names. The negative part of a function is still non-negative. So this is non-negative, this is non-negative. This expectation is finite, so each of these expectations has to be finite. So we know that expectation f plus x is finite, expectation f minus x is finite. Why do we know that? So since E of absolute value of f of x is finite, we have E of f plus x is finite, E of f minus x is finite. Similarly for G, I don't think you need me to write that out. Right? Similarly, expectation G plus of y is finite, expectation G minus y is finite. So far, so good? Yes? No? Questions? Okay, and now I'll basically ask myself, how do I take expectation of f of x times g of y? So what am I doing here? Here I'm taking a product of random variables. So of course, the first random variable f of x, I will decompose into positive and negative parts. That's f plus x minus f minus x. Second random variable g of y, I'll decompose into positive and negative parts. G plus of y minus g minus of y. So do you agree that you get f plus x minus f minus x multiplied by g plus y minus g minus y expectation? Any questions up to this line? Okay. And now you tell yourself, okay, let me expand this out. When I expand that out, I will get 4 terms, right? Now, remember a few things. Remember that we have already done steps 1 and 2. So this will be expectation f plus x g plus y minus expectation f minus x g plus y minus expectation f plus x g minus y plus expectation f minus x g minus y. Now, by the way, I have shamelessly split up the expectation into 4 pieces, and I can do that. Okay, why can I do that? Because I know that this is finite, this is finite, this is finite, and this is finite. Further, I know that this expectation, look carefully, is the product of this guy and this guy, both of which are finite. I've already done steps 1 and 2, remember. Similarly, I have, without any worry, written this out. Why have I written this out? Because I've done steps 1 and 2. So I know that this expectation is the product of this guy and this guy, both of which I know to be finite. Same with the third and fourth. So if you're wondering why we did not worry about just expanding the whole thing out, the answer is we have done steps 1 and 2. So we know that this expectation is a product of this guy and this guy, both of which are finite, and the same for each of these guys. All right, and then you just go through it, do the algebra. When the dust settles, you'll find expectation fx times expectation gy. Okay, let's just see what happens here. Here I have expectation f plus x g plus y. Now remember, you've done steps 1 and 2. So by step 2, for non-negative functions, this quantity, expectation of a product, is the product of expectations. By step 2, expectation of the product is product of expectations. Expectation of the product is product of expectations. Same here. Then there's just some silly algebra that you have to do. I'll leave it to you to check that you get E of f of x times E of g of y. Okay, so that's a big, nice thing about independence. If you have independence and you're taking expectations, you can without thinking twice. If you're taking expectations of something depending only on X, something depending only on Y, and X and Y are independent, without thinking if X and Y are independent, you can say expectation of whatever function of X multiplied by expectation, whatever function of Y. Any questions with this? All right, so let's move on to moment generating functions. You know, you've already been introduced to this through the problems, maybe on the test, the tutorial, something like that. You've already seen this. Okay, so let's just remind ourselves what is moment generating function. So suppose I have capital X, which is a real valued random variable on omega fp with law mu. Okay, so what does this mean? So this means X takes omega to R, right? This is a random variable. So this is f b of R measurable. And it has law mu. So that means for a Borel set A, mu of A is P of X inverse A, which of course I can also just write as P of X element of A. All right. Now I'm defining the moment generating function. Now remember the last time so the moment generating function of X is given by M of S is expectation e to the Sx, and this is for all S and R for which this expectation or integral is finite. Don't forget about this for a second. This much you have certainly seen. Let X be a real valued random variable on omega of P with law mu. The moment generating function of X is given by M of S is expectation e to the Sx, and this is for all S and R such that expectation or integral is finite. So far, so good? Okay. Now I have given this alternate expression here. Now my question for you is, why is this expression and this expression giving the same answer? Come on, anyone, why are these two guys the same? Is my thing volume very low? Gaurav, any thoughts why they are the same? Suman Kumar? Sanjukta? I'll give you a hint. We've already done this in class. I'm asking you, what have you done in class based on which these two guys are the same? That I'm hoping you can tell me. Anita? Ayush Anand? This is the basic change of variable formula, right? What did we do a few, I don't know, maybe 1 or 2 lectures back? Let's remember. Can you tell me how I'm applying this? Okay, that's a very straightforward question. How am I applying this proposition? So you saw what claim I made about the moment generating function, right? I defined it to be expectation e to the Sx. Okay, that is old news. And then I wrote it as integral e to the Sx d mu or mu dx. On what basis did I do that? The answer is here. I want you to tell me. Anita? Are you there?
Yes, sir.
Okay, how am I using this proposition in that claim I made about moment generating functions? The answer is very simple, so I must assume that perhaps you're not following because this is a very straightforward thing. How have I used this proposition? What choice of H will give me the claim I made?
Borel measurable.
Sir,
A Borel measurable has to be, but what specific choice of H will give me the claim about moment generating functions? How am I applying this?
real
It's
value
equal
of
to
random
e raised to
variable.
power sx.
Exactly. I'm just taking H. I'm just applying this, which hx equals e to the sx. That is it. Okay, I'm taking this thing here and I'm applying it for the special case that h of x is e to the sx, where s is some fixed number. Does that make sense? So
Yes, sir.
I am just applying this thing to the specific function h of small x is e to the small x, where s is some fixed real number. Okay, so that's how where did it go? That's how we got this. So here what I've done is I've basically taken h of x equals e to the sx, and then expectation of h of x equals the integral e to the sx mu dx. So this is basically the change of variable formula we had. All right. Now I claim we're saying that the domain of the moment generating function is the set of all real values of s for which the expectation is finite. Now, once again, this expectation and this integral are the same based on the proposition we just saw. Right, we saw a proposition, we said expectation h of x is integral e to the sx mu dx. Now, I claim that the domain of M may not be all of R. Okay. Can somebody give me an example of a random variable whose moment generating function would not exist? Okay, actually, let me go back. Is there any value of S for which this is absolutely guaranteed to be finite? So I'm asking you, is there any value of S such that no matter which random variable I take, this guy will be finite? Suman Kumar? अरे आंसर लिखा हुआ है यार. Zero, right? Because if S is 0, you have e to the 0, which is 1. Take any random variable x, e to the 0 is 1, so expectation of 1 is 1. So m of 0 is going to be finite for every random variable, no matter which random variable you take. Now let me ask you, can you think of a random variable where for other values of s, this may not be finite? Okay, I think you guys need to go back and look things up. Let me just go ahead. Okay, so I claim that for any random variable x, m of 0 is going to be finite. The reason is that, so indeed, no matter which random variable I'm talking about, m of 0 is the expectation of e to the 0. E to the 0 is 1, so this is just 1. So yes, m of 0 is finite for any random variable. Okay, now the next thing I want to say is the following. Integral e to the sx mu dx, right? This is the integral over r. This is the integral 0 to infinity e to the sx mu dx. plus integral minus infinity to 0 e to the sx mu dx. Why is this true? Well, integral of over the whole is the sum of the integrals over the parts. Right? Okay. By the way, can somebody tell me what are some properties of this function e to the sx? There are many properties, but can you tell me some properties? S is fixed. Gaurav, if you're saying something, you're muted, so I would not have heard it. What are some properties of the function e to the sx?
Sir, it is always positive.
It is always positive. Thank you. It is always positive. I mean, there are many properties. It is. So I'm fixing s. Okay. Fix s. E to the sx is always positive. It can never even get to 0. Forget going negative. It cannot even get to 0. So this integral is always going to be meaningful. It may be infinite, but it will always be meaningful. Okay. And this integral over the whole real line. This is an integral over the whole real line. This integral over the whole real line e to the sx mu dx can be written as integral e to the sx mu dx from 0 to infinity plus integral minus infinity to 0 e to the sx mu dx. Why? Integral over the whole is the sum of the integrals of the parts. Okay. So do you agree that this integral will be finite if and only if this is finite and this is finite? So integral, or let me just write it another way. Ms is finite if and only if integral 0 to infinity e to the sx mu dx is finite, integral minus infinity to 0 e to the sx mu dx is finite. Do you agree with that? All right. All right, so where am I going with this? Basically, I want to convince you that for any random variable x, the set of points where the moment generating function is finite is always going to look like an interval. Always. That's what I want to convince you. It's always going to look like an interval. 0 will always be there. In some cases, it may be just 0. In some cases, it may be a finite interval. In some cases, it may extend to minus infinity, but to some finite value here. Other cases, it may extend to infinity, but just up to some finite negative value. So the way we're going to do that is we're going to ask ourselves, when can we be sure that this integral is finite and this integral is finite? Okay, so I claim that the integral from 0 to infinity e to the sx mu dx is finite for all s less than or equal to 0. Why is this true? Why is this true?
Because if this is bounded by 1 and
Exactly.
integral of mu dx will always be between 0 and 1 because it is basically probability of something.
Exactly, right? So why is this true? This is true for the following reason. So remember that here, this is the integral from 0 to infinity. Okay, so here's what I'm saying. I'm saying fix s less than or equal to 0. Then this is definitely finite. That's the claim I'm making, right? So indeed, fix s less than or equal to 0. Okay. Note that for all x greater than or equal to 0, e to the sx is less than or equal to 1. Why is that? Because because sx is going to be negative. Okay. Okay. Let me note that for all x greater than or equal to 0, we have sx less than or equal to 0, and so e to the sx is less than or equal to 1. And so now we'll integrate. So the integral 0 to infinity e to the sx mu dx is less than or equal to integral 0 to infinity mu dx. Right? And remember, mu is a probability measure. So this is going to be less than or equal to 1 since mu is a probability measure. All right, so what we have shown is that when I'm looking at the integral from 0 to infinity, for all negative values of s, it's going to be finite. There's no danger of it blowing up. Okay, next claim I'm making is, I'm still looking at the integral from 0 to infinity. I'm saying that if the integral from 0 to infinity e to the sx mu dx is finite, for some positive value of s, then it is finite for any smaller value. Why is this true?
Because the function is strictly increasing.
Right, right. So let's write that out. So now note that here I'm looking at positive s, okay? Okay, so let's write this out. So suppose integral 0 to infinity e to the sx mu dx is finite for some positive s. Okay? Then for 0 less than t less than s and any x greater than or equal to 0, remember here the integral is from 0 to infinity. For any 0 less than t less than s and any x greater than or equal to 0, we have e to the tx is less than or equal to e to the sx. Again, we're dealing with non-negative functions. And so integral 0 to infinity e to the tx mu dx is less than or equal to integral 0 to infinity e to the sx mu dx. And of course, the right side is finite by assumption. Any questions with this? Okay, so basically what we've done is we've said that this integral in the moment generating function can be written as an integral over 0 to infinity plus an integral from minus infinity to 0. About the first part, namely the integral from 0 to infinity, we have figured out that that first part is always finite whenever s is negative or 0. And if it is finite for some positive s, then it is finite for any smaller s. Now, here there is a kind of mirror image of that argument. Okay, so now if you look at the integral from minus infinity to 0, e to the sx mu dx, one can show that for any s greater than or equal to 0, this is finite. Can someone tell me why? So I'm integrating from minus infinity to 0, so x has to be negative. If I take any s positive, then sx has to be negative, which means e to the sx cannot be bigger than 1, which means this function is dominated above by 1, and mu is a probability measure. Okay. Similarly, you can show that if this integral is finite for some negative s, then it is finite for all s less than t less than 0. So let me just go ahead and draw a picture. So this is actually the s-axis. Okay? What have we shown? We have shown that if you look at this integral from 0 to infinity e to the sx mu dx, we have shown that it is definitely finite. No, that's too big. It's definitely finite over here, right? We have already shown that. And we have shown that if it is finite somewhere here, then it's finite to the left of that. Correct? And if it's finite here, then it's finite to the left of that. We have shown that. In other words, what you're expecting is that you'll have an interval. It'll definitely contain the whole negative axis. It'll contain 0, and it may or may not contain some positive numbers. But if it does contain some positive numbers, there will be an interval. Similarly, if I look at integral minus infinity to 0 e to the sx mu dx, I have just shown that this integral is finite for any s greater than or equal to 0. So over here is definitely finite. And we have shown that if it's finite here at s, then it's finite here at t. In other words, again, you're expecting that this is what the picture might look like. Does that make sense? So the highlighted part is the set of all values of s where that integral is finite. So if I look at this integral, it is definitely finite for all s negative. If it is finite for any positive s, it is finite for smaller positive values of s. So maybe it's only finite here and 0. It's okay. But if it goes to the right, then everything, this should be an integral. Similarly, this integral is finite for all s greater than 0. If it is finite for any negative number here, it's finite for any bigger negative number, which is a negative number smaller in magnitude. So for both these integrals to be finite, you can imagine what should the domain look like. It should look like an interval, right? If you look at the intersection of the two highlighted thingies as basically an interval. So what we're saying is that, okay, so by the way, another possibility here, just to be clear, another possibility here is this. Okay, and the green is another possibility. It is only finite for s negative and at s equals 0. That's it. You guys with me? And the third possibility, of course, is that it is finite everywhere. Right? Are you guys with me? Is this making sense? In this case, you could have a situation where basically these are the possibilities. Right, the yellow case corresponds to the case where this integral is finite for all negative s and some positive s's. The green case is where it's finite for all negative s's, for s equals 0 and for no positive s's. That could also happen. And the blue case is when it's positive for all negative and all positive s's. This integral, the yellow case is the case when it's positive for all positive, it's finite for all positive s and some negative s. The green case is when it's positive for s equals 0 and only positive s. And the blue case is again is when it's finite for all possible s. So basically look at this picture, look at yellow intersect yellow. What are you going to get? You'll get a finite interval containing 0. Now take yellow intersect green. What are you going to get?
Some interval which is not finite.
So loudly, volume upper karo yaar, thoda. What did you say? Some interval?
some interval which is not finite. So infinite interval.
No, okay. Then maybe I need
So
to
can you
draw.
repeat, so can you repeat the question?
Okay, should I just, you highlighted, can you see the highlighted stuff or has it all been over? Can you see clearly?
So the yellow part is not visible clearly.
Yellow part is not visible, right? So let's fix that. Okay. So far, so good. Okay, now I'll take a smaller size and then I'll draw the green. Can you see the green here? Visible or no? Should I get a different color? Can see this? Okay, is this picture visible now? Okay,
Yes.
yes? Okay, so now what am I saying? If I look at this integral 0 to infinity e to the sx mu dx, the set of all s's where this integral is finite has to look like one of these three. Can't be anything else. It is either finite only for negative s and s equals 0 and infinite for positive s, or it is finite for all negative s's for s equals 0 and some positive s's which look like an interval, or it is finite for all real s's. If you look at this integral minus infinity to 0 e to the sx mu dx, there are exactly three possibilities. One is that it's positive for all s positive for s equals 0 and some negative s's. It's finite for all positive s's and s equals 0 and infinite for negative s's. And it's finite for all s's. So far, so good? Okay. So now in the first case, you can have any one of these three. In the second case, you can have any one of these three. The domain is going to be the intersection of the two. Agreed? So if I take yellow intersect yellow, what is that going to look like?
Finite length interval.
Okay, and instead tell me a little more. What property will that interval have?
It containing 0.
It's containing 0. It's an open, it'll definitely contain 0. Let me draw it somewhere up here. It's going to look like that. Okay, that's not the right size, but it'll look like that. Agreed? That is, it'll contain 0. Suppose it is yellow intersect orange here, then what are you going to get?
Sir, only 0.
So
Close to
finite
0
length
and
interval which
open to
contains
some
0.
positive real number. Close
Right.
to 0 and open to some positive real number.
Right, so now I'm saying take yellow here and take orange here. So what is in the intersection is, you guys said it right, it's 0 and some positive numbers.
Yes, sir.
Now blue is easy, right? Because if I take blue, no, if I take blue here, blue intersect anything is going to be the other thing. Right? And now suppose I take orange intersect orange, what am I going to get?
Only 0.
Just 0, right? In that case, I will only get, the thing is finite only at 0 and nowhere else. Anyway, you can play around with this, but hopefully this gives you an idea that no matter what happens, the domain of definition is going to be an interval. It may be a degenerate interval, it may contain only 0. It may be infinite, it may be infinite on both sides. Okay. All right, so that's what we're saying here. Putting the above pieces together, and we have hopefully done it in this picture. It follows that m of s is defined on some interval containing 0, and just a matter of terminology. Here, when we say interval, we are allowing a single point interval. So we are allowing that the interval is degenerate, namely just contains 0. All right, now this thing I have already done in the picture. So if x is non-negative, then the interval over which m of s is finite contains all of minus infinity 0 and perhaps part of 0 infinity. This we have already seen, because if x is non-negative, then the MGF is entirely given by this. The other term is gone. Because if x is non-negative, then its law mu will be 0 to the left of x equals 0. So if x is non-negative, then this thing that I've circled, this is going to actually be m of s. So it'll be finite for all negative s's and maybe for some positive s's. Similarly, if x is non-positive, namely it is 0 or negative, okay, so similarly, if x is non-positive, then the interval contains all of 0, infinity, and perhaps part of minus infinity 0. All right, so enough about this. I don't want to get into this anymore. If something is not clear, I'm sure you'll have a chance to look over the recording and the notes. Let's move along. Now, of course, this is called moment generating function, right? You may ask, why is it called moment generating function? So let's just do that before. So what I want to do is next, I want to do some proofs, but before I do that, let's just talk about why this is called moment generating function. So this is the question. Why is it called moment generating function? Does anyone want to take a guess at that? Actually, can somebody tell me what is the third moment of x by definition? I'm not asking you to calculate, I'm just asking you by definition, if somebody stops you in the mess today and says, oh, Anita, what is the third moment of x? What are you going to say? Gaurav, what will you say if somebody asks you what is the third moment of x by definition?
So the expectation of x cube.
Expectation of x cubed, right? Okay. So I'm calling this moment generating function. Does anyone want to guess why I'm doing that? Let me give you a hint. Suppose I were to differentiate both sides and play around a little bit. What might I be able to do? Okay, so suppose I differentiate both sides. Okay, so this is so I'm writing heuristic. So this is not rigorous. Okay, this is not rigorous. This is not a proof. Here we're just boldly doing some calculations and hoping that they will work. Okay, so suppose I take the derivative m prime s. This is going to be expectation of what? X e to the sx. Agreed. What is m prime of 0? Expectation of x. M double prime s is going to be expectation of x squared e to the sx. M double prime 0 is e of x squared. So you see the pattern, right? If I take the nth derivative of m evaluated at s, I'll get expectation x to the n e to the sx. So the nth derivative of m at 0 is just expectation of x to the n. So now do you see why the name moment generating function is there? Right? Because if you want the fourth moment, you take 4 derivatives, set s equals 0, that's your fourth moment. If you want the second moment, you take 2 derivatives, set s equals 0, that's your second moment. Hence the name moment generating function. All right, now just to be clear, you cannot just blindly do this. You need some technical assumptions to do all this. But if the technical assumptions are satisfied, then you can do this. So thus, let me put that in red. Okay, so you cannot just do it. It does require certain technical assumptions. Okay, but the point is, if you have those technical assumptions, then you can get all the moments of x from the moment generating function by taking the appropriate number of derivatives and then plugging in s equals 0. Okay, hence the name moment generating function. Questions so far? All right, so remember, you cannot just blindly do this. Some conditions need to be satisfied. So let me tell you what conditions need to be satisfied. If the moment generating function, if the domain of M contains a little interval containing the origin, doesn't matter how small that interval is, then you can safely do this. Okay, so you know that the MGF for any random variable is always going to be finite at s equals 0. If it's finite, even a little bit here and a little bit here, in other words, if it's finite in a small interval containing 0, then yes, you can do all this without worrying. It doesn't matter how small or big that interval is. Okay, so that's what this proposition says. So here's our proposition. So let x be a real valued random variable on omega fp with log mu. All right, now as before, we are defining the moment generating function. Suppose that m of s equals expectation e to the sx. This is the moment generating function. Suppose this is defined for all s in the interval minus s0, s0 for some s0 greater than 0. So we're making the assumption that in some interval containing 0, the moment generating function is defined. We are not going to be concerned with whether this interval is small or big. We're not going to be concerned whether it's infinite on this side or whether it's infinite on this side or whether it's finite on both sides or whether it's infinite on both sides. As soon as you know that in some open set, as soon as you know that in some open interval containing s equals 0, the MGF is finite, you can safely do all this. That's what this proposition is saying. So suppose that ms equals expectation e to the sx is defined for all s in the interval minus s0, s0 for some s0 greater than 0. Then the claim is then x has finite moments of all orders. And further, m of s, the moment generating function, can be written as this sort of Taylor series, or I guess Maclaurin series. ms is some k going from 0 to infinity, s to the k divided by k factorial expectation x to the k. Now again, why is this intuitive? This is intuitive because remember, expectation of e to the sx is going to be expectation of some n going from 0 to infinity. What am I going to get? S to the n, x to the n over n factorial. That's what you have. All right, and basically what they're saying is that if ms is finite in some interval minus s0, s0, then you can interchange this summation and expectation. Okay. So the claim is that x has finite moments of all orders, and m of s is the sum k going from 0 to infinity, s to the k over k factorial, e of x to the k. And further, expectation x to the k is integral over r, x to the k mu dx, which is mk of 0. Any questions with what we're saying? Okay, so now here's what we'll do. We'll go ahead with the proof of this, but to finish the proof, there's a certain lemma that is needed. That lemma we'll have to do next time. So somewhere in the proof, there's going to be a small hole, okay? And that hole needs a lemma. That lemma we'll do next time. I want to do it this way because otherwise I may do a lemma and somebody may say, why are you doing this? Well, so why didn't I show you where you need the lemma and then we do the lemma? Okay. So here's the proof. So note that e to the absolute value of Sx is less than or equal to e to the Sx plus e to the negative Sx. Do you guys agree with that? What is absolute value of Sx going to be? There are only two choices. It is either Sx or it's minus Sx. So e to the absolute value of Sx. If the exponent here is Sx, then left side is equal to e to the Sx. If it is minus Sx, then it is equal to minus Sx. In either case, it is less than or equal to the sum of those two. Okay. And it's like I tell you, I have a number in mind, and I tell you that the number is less than, the number is either, let's see, I'm going to mess this up maybe. I have a number in mind, and I tell you the number is either 4 or it's 3. Well, you can be sure that the number I have in mind is less than or equal to 4 plus 3, right? That's not a perfect analogy, but that's what I'm saying here, right? This quantity takes either this value or this value. So of course, one thing is true is this guy is less than or equal to the maximum of these two. Agreed. That is also true. But another way of saying that is that this is less than or equal to the sum of these two. So that's what we're doing here. So note that note that e to the absolute value Sx less than or equal to e to the Sx plus e to the minus Sx. Okay, also by assumption, integral e to the Sx mu dx is finite, and integral e to the minus Sx mu dx is finite for mod S less than S0. I'll just leave it to you to play around with this a little bit. Here I know there is Sx and here there is minus Sx, but remember in some interval around 0, these guys are finite. Okay, so what you get is, now you get integral e to the absolute value of Sx mu dx is finite for all mod S less than S0. In other words, e to the absolute value of Sx is mu integrable for mod S less than S0. Mu integrable means just integrable with respect to mu. All right. So e to the mod Sx is mu integrable for mod S less than S0. And now I'll take e to the mod Sx and I'll write down the power series. Right? So this is going to be the sum k going from 0 to infinity, mod S to the k, mod x to the k over k factorial. Right? Now here I have an infinite series and every term is non-negative. So the sum of the series has to be bigger than every term. Right? If you add up a whole bunch of non-negative numbers, the result has to be bigger than each of the numbers you added. So this has to be greater than or equal to mod S to the n mod x to the n over n factorial for any n. You guys with me? If I'm adding 10 non-negative numbers, the sum has to be bigger than each of the numbers I added. Okay, so this has to be true. So this is true for any n. So what does that mean? That means that, let me look at this thing. Actually, let me look at this thing. So I'll get mod x to the n is less than or equal to n factorial e to the mod sx over mod s to the n. This is for some fixed n. So now non-negative function, and you know that integrals of bigger functions cannot be smaller. So integral mod x to the n mu dx is less than or equal to n factorial over mod s to the n integral e to the mod sx mu dx, which is finite. And because we have shown that this guy is finite and these guys are just some numbers. So what we have shown is that this integral is finite for 0 less than s less than s0. Are you guys with me? Okay, so what you get is you get that expectation. Now, what is this thing? This guy is simply expectation of mod x to the n. Right. All right. So what you get is you get that expectation mod x to the n is finite for all natural numbers n. In other words, we have shown that all moments of x exist. Okay, so now what I'm going to do is, here is where I'm going to use a lemma below. So using the lemma below, we have, and I'm showing you where you need the lemma. So ms is expectation e to the sx. So far, so good, right? This is just definition. Then this thing is also natural, right? E to the sx, I can write as some k going from 0 to infinity, s to the k, x to the k over k factorial. So this equals this, fine, I hope. This equals this, fine, I hope. That expectation is outside this exponential I've written as a sum. Now what I want to do is I want to interchange the summation and expectation, and here is where I need the lemma. So this lemma below, which we'll do next time, is going to guarantee that I can interchange the expectation and summation. Suppose I believe the lemma. Then I'll get some k going from 0 to infinity, s to the k over k factorial, e of x to the k, right? And what is this going to give? This is going to give some k going from 0 to infinity, s to the k over k factorial. Remember, e of x to the k is just the integral over r x to the k mu dx. Why are these two guys the same? I've asked you a version of this question earlier today. Why are these two guys the same? Why are these two things the same?
We put h is equal to
Exactly.
x raised to k.
Right, exactly. Basically, you take h, the function h is x to the k, right? So that's exactly what we're doing here. All right, so this thing, so I'll get some k going from 0 to infinity, s to the k over k factorial, integral over r x to the k mu dx. And this is for mod s less than s0. So what do we see? Right? We see that m of s has a Taylor series expansion about s equals 0 with a positive radius of convergence. And now you use certain facts about Taylor series. Right? If you have a Taylor series on an interval and it converges inside the interval, then inside the interval you can differentiate as many times as you like. And the derivative is given by just differentiating the series term by term. So now we are using that. So thus, ms has a Taylor series expansion about s equals 0 with a positive radius of convergence. So now some of the facts we're using are about Taylor series. Okay, so now we use the fact about Taylor series that ms is differentiable for mod s less than s0. This is not a statement about probability. This is a statement from basic real analysis. If I have a Taylor series which converges in a certain interval, then inside that interval you can differentiate as many times as you like. And further, the jth derivative is obtained by just differentiating term by term. Again, this thing involves probability, but this fact is basically just about Taylor series. The jth derivative of the Taylor series is obtained by differentiating the series on the right side j times. I'll leave it to you to check that this is the actual expression you get. Okay. Some k going from j to infinity, k minus 1 all the way up to k minus j plus 1, ex to the k over k factorial s to the k minus j. And now at this point, I'll plug in s equals 0. If I plug in s equals 0, what is going to happen is, if I look on the right side, a series goes from k going from j to infinity, and there's an s to the k minus j. So if k equals j, then this guy is going to just equal 1. If k is greater than j, and I put s equals 0, then this guy will disappear. So if I take mj of 0, I'll just get expectation x to the j. I'll leave it to you to check that. So in other words, what we've shown is that for every natural number k, the kth derivative of m evaluated at 0 is e of x to the k. So we have seen that in this case, moment generating function is a Taylor series, positive radius of convergence. It is infinitely differentiable. Derivatives are obtained by differentiating just term by term. And these kacha calculations that we did, they actually work out. Okay. So the sufficient condition for that is that absolute value of S has to be less than S0 for some S0. There's one hole in the proof which we need to fill in. Here I assume that expectation of this sum of the sum of expectation. This I still have to justify. We'll do that next time. All right, any questions?